基本上还剩下3周可以教的时间，然后在第4周可能就要考试了，好，然后所以时间有点短，所以我可能得省略一部分内容，快教到第7章。好，我今天先赶快把第5章结束掉啊。So today we continue to teach chapter 5, and I think I can finish chapter 5 today, and I can also teach a little bit the final part of chapter 4, and then I will teach chapter 7, and in about the middle of December, I will have the final exam. 好，那我们上次讲到这个Body Stokes filter 还没有完全结束掉，还有一点点。So last time we talked about the Body Stokes filter. The Body Stokes filter consists of a series of wave plates a pair of wave plates consists one period in the series of wave plates. Then we can they are arranged according to the rule that the first wave plate has an orientation along positive rho, and second has minus rho, and repeat this orientation arrangement. And then the totally n piece of wave plate, n is equal to 2m. n is the total number of periods. Then we can write down the matrix representation of this wave plate series, which is the product of the nth power of the product of W minus rho and W rho. Here, W rho is this. W rho is this R minus rho, W0 R rho, and here W0 is this matrix. And then according to Chebyshev identity, we can write down the matrix M, and the first there is a polarizer PX polarizer alone before the light entering into this series of wave plates, and finally we have a analyzer EY. Okay, and then what is important is to calculate M21, because the final Y component EY is related to the X component of the incoming wave. Okay, and use this, we can write down the transmittance as the absolute value of M21. And then according to Chebyshev's identity, we see that the result is sine 4 rho sine square half gamma sine m theta over sine theta squared. Okay, here cosine theta is defined as 1 half a plus b. Here a is a and d. A and D are the diagonal elements of the matrix. Sorry. This. Okay. The product of M W minus rho and W rho I denoted as capital omega. The diagonal elements of capital omega are A and B. Okay, and this F power is being denoted as M. Okay. And then finally we need to calculate M1. And according to Chebyshev identity, M21 is equal to this. And here, cosine theta is defined as the trace, 1 half the trace of the capital omega. Okay. And then we use this transformation to define theta as pi minus 2 pi. Then we can change our variable from theta to pi. And here we find cosine pi is equal to cosine 2 rho sine half gamma. Then substitute this result into this t. We finally find the result is this one. This one. Here we find that we should set rho equal to pi over 4n, so that when gamma is equal to gamma is equal to pi, then this rho gives us the result that the wave can completely penetrate through this device. Okay. Then we substitute this rho into this expression, and we find that when gamma is equal to pi, t is equal to 1. However, we need to analyze the behavior of the curve of this t transmission. So we assume that gamma takes the value of odd number times pi plus something. This delta gamma is a very small quantity compared to pi. Okay. Then when we substitute this expression into this formula and using this relation, we can find an approximate expression of this transmittance T, which is equal to this. T is this one, sine half pi square root 1 plus n delta gamma over pi squared over this. Okay. This function has a form very similar to the so-called sinc function, but it is not exactly the sinc function. a sinc x is defined as sine pi x over pi x. This is the so-called sinc function. Sinc function appears in optics textbooks, okay? And sinc function has this property that when x is equal to 0, it has the highest value. Then it decay and vibrate it has this kind of shape. Okay. The function, this function is not sinc function. It is always positive, but it has similar behavior like sinc function. Okay. This kind of shape. Okay. Then suppose this here is pi. We use gamma over pi as the variable. Then here we have 1 gamma over pi. 1, 2, 3.然后呢，它是这样。Okay. Around the odd number times pi, around the if gamma takes the value 2 nu plus 1 time pi, nu is an integer. Nu is an integer. nu是一个整数的时候，2nu加1是一个奇数，对吧？然后呢，2nu加1派是一个奇数倍的派啊。我们绕着奇数倍的派附近去看，它都会长成这个样子啊。Around the odd number times pi, the t term looks like this. And we want to analyze the specific shape of this curve. We assume delta gamma is small. Then we find this formula. According to this formula, you can easily plot this curve. Okay? Then the highest value of the t is equal to 1. And if we want to know what is the height of the saddle, okay, the second peak, we want to know the height of the second peak, then we need to do a little bit analysis. We see that here, if we take n, if we take gamma to be 0, then this is sine half pi, which is 1 over 1. So we have this value 1. And then if delta gamma, if this quantity becomes 2, then we have sine half pi times 2, which means sine pi is equal to 0. So we get this 0. Okay, we get this is 0. And if this part, if this is equal to 3, we have sine 3 second pi. Okay, the 2/3 pi, which has the absolute value equal to 1. So it goes to this point. Okay, because now its height is equal to 1 over 3 squared. 就变成这样子啊。When delta gamma satisfy this condition, we get this x. Okay. 好，那如果这边给出偶数的时候，我们就刚好得到0嘛，对。So if 0，就刚好降到最低点啊。0的时候，如果是偶数的时候，就降到最低点，因为偶数乘上2/π就是整数倍的派，sin整数倍的派就是0。但如果sin 2/7数倍的派，那绝对值就等于1啊。所以绝对值等于1的地方得到 peak， 然后呢，如果绝对值等于0的地方就得到0最低点。对啊。那除了这个之外，我们还想知道说这个 peak 有多宽。We also want to know the width of this peak. We can calculate the so-called 半高宽啊，半高宽是 F W H M halfway height maxima 啊，就在 half maxima 啊。半高的宽度了啊 ，full width 啊 ，full width of half maxima。Okay, so we can find these 2 points, and here these 2 points correspond to p equal to 1/2, and calculate the width. We treat this width as the width of the peak. OK， 好，所以呢，这边呢。我们就数值方法上可以去找到啊，这个直接这样看不太出来啊，用数值方法去找啊。We can calculate this result numerically, and then according to my calculation, we have delta gamma positive negative, which is equal to positive negative 0.8 pi over n, approximate result. This is the approximate result. then the width delta gamma is equal to 1.6 pi over n, which is equal to the difference between delta gamma plus and delta gamma minus. Okay, and this we see that since gamma is equal to 2 pi over lambda times Ne minus No times d. D is the thickness of one wave plate. Then we see that delta gamma, we can write delta gamma as d gamma over d lambda times delta lambda. Okay. This is an approximate solution because this is just the Taylor series. Okay. And d lambda, d gamma is equal to minus 2 pi over lambda squared times Ne minus No times d and times delta lambda. Okay. If you compare this with gamma, you see that this is minus 1 over lambda gamma nu. Here we take the value lambda nu. Lambda nu means the wavelength corresponding to gamma equal to 2 nu plus 1 pi. Gamma nu means 2 nu plus 1 pi. Okay? Here. Nu plus 1。对，好。好，这边 L 如果等于0的时候，就是这个主 peak 啊 ，L 等于1、2、3就是其他的 peak 啊。好，那所以根据这边的话呢，你其实可以把这个移过去啊。 然后来算出这个delta lambda 啊，就这两个之间的关系是这样。So now we take the absolute value of this formula. We see that delta lambda is equal to lambda nu over 2 nu plus 1 times (1.6 pi over n). Okay, which is equal to 1.6 我想，刚刚那个delta gamma，等我一下。哎，等一下啊，这边少了一个拍了，这边少了一个拍啊。So here we have pi here. So this pi cancels with that pi. We get lambda nu over 2 nu plus 1. And, okay, this is the resolution formula. This formula means that the resolution 啊，就是说我们可以找到那个波长呢多么接近这个中心点啊。The central wavelength is say lambda nu. Then only when we choose the wavelength close enough to this peak will we get transmittance large enough to be observed. 啊，就说我们透过这个所谓的滤波器呢，我们会发现说哦，那如果波长差太多的，它就被滤掉了，对不对？那波长非常接近这个值的，它就穿过了，啊，所以这个就是说，我们在那个波长的选择上呢，当然是那个我们想要抓到那个非常精准的那个波长，啊，所以这就牵扯到一个解析度的问题，啊，那这个解析度这边对应到这个波长的误差呢，这个德尔塔浪塔就是这样一个公式，啊，那现在的问题是说，好，那假设我真的想要它非常非常的精准，啊，那要精准到什么地步呢？我们假设想要让这个解析度落在1 Armstrong 啊，就是 1 Armstrong. If we ask the delta lambda to be within 1 Armstrong, which means 0.1 nanometer, and we choose lambda nu to be this nanometer， 是一红光了啊。那这时候呢，我们需要多少片 ？How much pieces waveplane do we need to use? Okay, then this means that 1 is equal to 1.6 times suppose we take nu equal to 0, and this formula gives this relation, and this relation means n is about 10,000. OK， 就是说，如果我们的解析度要到1 Armstrong， 我们的操作波长是这个波长啊，那我们要用多少片 waveplane 来做出这个 Bode-Sok filter？ 答案是大概10000片。OK， 好，大概10000片啊。So we need about 10,000 pieces of waveplanes to make this filter, so that we can have the resolution about 1 Armstrong operating at this wavelength frequency, this wavelength. 好，这是 Bode-Sok filter 啊。And corresponding to this position, what is the value of the transmission? The height of the transmission is 1/2L plus 1 squared. OK， 所以它的这个值呢就变成，这是1，这是1/9，这是25/1，好，然后10类分，它的高度就这样子依次递减，好，13579的平方，好，这是 Bode-Sok filter。现在我们再看另外一个情况，叫做 Fan-Sok filter。Now we consider another filter, which is named as Fan-Sok filter. Fan-Sok filter, there we have px wave plate, and the first piece, the orientation is rho. The second is 3 rho, and finally we have pi minus rho. Okay. And then here we have horizon px. Different from the full dissolved filter, here we use two wave plates whose orientation is along the x-axis. The transmission axis is parallel to the x-axis. Then its mathematical description is this one. M is we name the product of all this wave plate as M. Then M is written as R minus half pi plus rho W0 R half pi minus rho minus 3 rho W0 3 rho minus rho W0 rho. Okay. So you see here we can write this as the product of this give us 2 rho. Okay. And the final part, R rho, can be written as 2 rho times R minus rho. Okay. And so we can write this as R minus half pi plus rho. Total number of the wave plates is n. We can write this W0 R 2 rho n the power times R minus rho. This part you can use Chebyshev's identity. Then you multiply this result with minus rho and minus half pi plus rho. Okay. In fact, you can also write this result as you see R2 rho can also be written as R rho times R rho. So this M can also be written as R minus half pi times R rho W0 R rho n power. In this way, you need only to calculate the n power of this combination times minus half pi. Okay? Both expressions are equivalent to each other. And now we see that suppose we send a beam of unpolarized light into this device, and after penetration to the polarizer, it becomes 0 degree polarization, which means the X polarized light. Then X polarized light, when penetrating through this rho polarized transmission axis along the direction rho, then if we set gamma equal to pi, if we choose gamma equal to pi, then it becomes 2 rho oriented. Okay, 0 rho polarization becomes 2 rho polarization, and 2 rho encounter this wave plate 3 rho. Then it becomes 4 rho. Okay, 2 rho, 4 rho, and this becomes half pi orientation. Okay, the half pi orientation, half pi Y polarization will be blocked by PX. The X polarized will blocks this Y polarized light. So we see that the highest value transmittance for Folded-Soak filter corresponds to the lowest value of transmittance of Fan-Soak filter. Okay. 就是说那边在 Folded-Soak filter 里面，穿透率最高的地方就是1的地方，刚好对应到 Fan-Soak filter 穿透率最低，就是完全被 block 掉，完全是零穿透的情况。Okay. However, if gamma is equal to 2 pi, then the originally X polarized light will not be changed and keep the polarization unaltered through the whole device and finally penetrate through the final analyzer and get the transmittance equal to 1。就是如果说伽马等于2拍的时候，它就长驱直入完全没有被挡住，然后最后痛哭所以你看这个Folded-Soak filter 在拍3拍5拍地方是完全穿透，然后 Fan-Soak filter 是在这个0拍2拍0拍2拍没有，其实没有其实没有0拍这个东西2拍、4拍、6拍的地方完全通过。OK. And we can calculate this result just like we did before for the Folded-Soak filter. But now we need to calculate not M21 matrix element, but M11 matrix element. Okay. Now we need to calculate the M11. And M11 is given by this sine 2 rho cosine half gamma. Okay. Sine n chi sine chi. Here cosine chi is cosine 2 rho cosine half gamma. Okay. This relation is different from the previous relation of chi for Folded-Soak filter. Okay. Then now we need to calculate M11. Okay. and the result is tangent to rho cosine chi sine n chi sine chi squared. Okay. And as I have already explained, when we choose gamma equal to 2 nu times pi, we get p equal to 1. Okay. You can try to substitute here. When nu is gamma is 2 nu pi, half gamma is nu pi, and cosine nu pi give us positive or minus 1. This means that we can choose chi to be equal to 2 rho. Then here sine chi over cosine chi is nothing but tangent chi. Okay. When cosine chi is equal to positive or negative cosine 2 rho, then tangent chi is equal to positive or negative tangent 2 rho. And this means that these two terms can cancel in the absolute value sign. Under this, just if we ignore the positive or negative sign, okay, they can cancel with each other. And this sine n chi can be replaced by sine n 2 rho. Sine 2n rho. However, rho is pi over 4n, so this is equal to sine half pi. Okay, and sine half pi gives you 1. So this absolute square gives you 1. Okay, and now we need to analyze the behavior close to this specific gamma, just like we did before for the Bode-Sok filter. So now we see that gamma nu is equal to 2 nu pi, and we can write down the delta gamma. We can write down delta gamma plus minus two nu pi over lambda nu times delta lambda. Okay, and now we have this relation. Cosine chi is equal to cosine 2 rho times cosine half gamma. Okay. And we see that this is equal to cosine 2 rho times gamma is equal to 2 nu pi plus delta gamma. Okay. And this is cosine nu pi plus half delta gamma. Cosine nu pi gives us minus 1 to the power of nu times cosine 2 rho times cosine half delta gamma. Okay, and here we can choose chi to be we can choose chi to be some mu pi plus chi delta. Okay, here chi delta is a small quantity, and this gives us this fraction. So we can write down the result as cosine chi delta is equal to cosine 2 rho times cosine half delta gamma. Okay, both 2 rho and half delta gamma are small quantities. 再给我1分钟。Then since all these 3 quantities are small, we can Taylor expand them to the square term and compare the square term. Then we will see that chi delta square can be written as 2 rho square plus half delta gamma square. Okay, and so chi delta can be written as 2 rho times this delta gamma over 4 rho square. Okay, and this is pi over 2n, and this is 1 plus delta gamma over n pi square. Then we can play the same game again. Okay, and to see what is the shape of this transmission curve. 好，我们在这边先下课一下。We have this relation and we know that now chi delta, 2 rho, and delta gamma are both small quantities. Then according to the Taylor series expansion formula for cosine theta. Cosine theta can be expressed as 1 minus 1 half theta squared. Okay? The higher order terms can be ignored because we do not test the accuracy to be so high. We can keep only up to the square term. Then this can be written as, the left hand side can be written as 1 minus 1 half pi delta square, and the right hand side can be written as this. Okay. The multiplication of the right hand side gives us 1 minus 1 half the sum of 2 rho squared and half delta gamma squared plus fourth order term. However, this fourth order term can be ignored because we get only up to the second order term. Okay, so this finally gives us this relation, and according to this relation, we can write down this. And here we use the rho equals to pi over 4n. Okay. And according to this, now we can see that the transmission formula, is this tangent to rho tangent pi psi n chi squared, and this can be written as I can since replacing chi by chi delta can give us only plus or minus sign, so this can be replaced as chi delta, okay, and this can be replaced by chi delta, and since now chi delta is a very small quantity, we can we know that tangent, say epsilon, if epsilon is very small, can be approximated by epsilon. Okay, then so this means that now this can be replaced by 2 rho over chi delta times psi n chi delta squared. Okay, and we see that here 2 rho over chi delta give us this vector. And now psi is n times chi. N times it gives us half pi times this. Okay, so we see the formula is the same as before, as the approximate formula for Bode-Sutton filter. The only difference is the position or location of the peak. Okay. For the Bode-Sutton filter problem, the peaks located at other number times pi. Okay. However, for Fan-Sutton filter, these peaks are located at even number times pi. So we say gamma. And just like before, we can write down the resolution formula like this. Here, 2 nu plus 1 will be replaced by 2 nu. And we have the same requirement for the number of wave plates to get the required resolution. 跟从前的状况其实一样的也是，比如说要达到那样解析度，也是要1万片1万片左右好，然后这时候呢，它的这个 transmission 的图呢会长成这样 here is 0, here is 2. 2 ，OK， 好，这是偶数了啊，偶数被人拍的地方啊，刚好是偶数被拍的地方，啊，出现 pick。好，这样我们就把这个folded soak filter 跟 fed soak filter 基本上算讲完了。好，那接下来的这一节的内容呢，其实可以看成是 fed soak filter 在wave plate 的数量变成无限大时候的一个呈现啊，探讨的是易经的问题啊。我们这边要探讨的是这个下列型议题。For the magnetic liquid crystal, you can treat this medium as a multi-layer medium. Okay, in each layer, the molecule has the axis along certain direction. Okay. Then in the next layer, the orientation becomes a little bit different, and then a little bit different further. Then we can treat them as a series of wave plates. Okay. Then this is just like a fed soak filter. In the limit of n approaches infinity.好，就是说，我把它当成是好像 fed soak filter 的一个极限状况啊。那 fed soak filter 你可以分出它是一片一片，是真的就是人去安排的。但是这个下列型易经呢，你可以让它你可以安排让它这个分出一层一层的一层一层的这个分子的指向呢是慢慢变化，慢慢变化。那我们如果把它当成连续的变化的时候，它相当于是 fed soak filter 的片数变成无限多，这样一个极限状况。So we can treat the liquid crystal as a multi-layer structure. Each layer can be treated as a wave plate, and we can model it by a fed soak filter. And the only difference is that now we can treat it as n goes to infinity, the fed soak filter. So now we need to find how to calculate the n goes to infinity result, okay, for the fed soak filter. 所以我们现在呢，就是 来研究呢，如果 n 趋近无限大的时候的这个 Fan-Soak filter 公式，我们能不能得到一个解析的形式然后比较好去分析它，来帮助我们理解这个易经的这个穿透特性好，那方法是这样子的The method is that if we denote this direction of the z-axis and the orientation, the angle of the molecule is denoted as psi z equal to some constant times c. Alpha is a constant which determine how fast the orientation change by the deep depth by going down, OK， 然后伽马呢？Now we denote gamma as the total retardation of the假设我们易经全部的厚度这么厚的话，我们现在伽马不是代表一片的伽马，而是整体的伽马就是说它是一整个厚度的这个因为你现在分子呢是有一个长的方向跟一个短的方向那所以它会有这个所谓的 retardation 就跟我们之前的 wave 一样那现在就是说，假设你安排让它每一层的分子都指向同一个方向的时候你去看它的这个 retardation 长轴跟短轴方向的折射率的差所造成的伽马的话就是这个伽马就是这个伽马This gamma is for the whole structure, not for one single layer. Okay. This gamma is equal to 2 pi over lambda times Ne minus No times L. L is the thickness of this liquid crystal. And the total phase, total angle, total rotation angle is equal to the psi L, which is equal to alpha times L. Okay. 好，就整个厚度，你让它转那个分子的指向总共转了这么多角度alpha L 角度那我们现在呢，怎么来用这个 Fan-Soak filter 去写出这个结果来答案是这样子，就是我刚刚其实有解释过我们的第二种方法Using this representation, we can write this as M等一下No, use this representation. This we use this formula, but now we replace 2 row by row, and remember that now the total number is going to infinity. Then M can be written as 我们最后的那个并不见得是转到负2分之派加 ρ 这里，因为我们的 Fan-Soak filter 是那个 wavelength 真的最后方向是转到2分之派，但是我们现在的易经呢，可以转到某个角度就好，转到 phi 就好 we now rotate the transmission axis to phi, not half pi. So here m can be written as this. Okay. Here rho means phi over n。我们现在是这个，我们总转角度是 phi， 然后总共有 n 片，所以每一片转了 n 是 phi。啊，我们之前那个 Fourier Transform filter 是每一片转二 rho， 但是我们现在每一片让它转一个 rho 就好。 那转了 n 片之后，总共转了 phi， 所以一片转了 rho 等于 phi 这边。啊 ，so some notation difference, but the whole structure, the whole calculation is in fact the same kind. OK， 好，好，我们可以写成这样子的 n 次吧，这样 n 次。 那这边我要跟大家讲一下课本的符号呢，跟我的符号有一点不一样啊。就这个正负号呢，我跟课本的有点不一样啊。那我认为我的才对啊。那这个，但是呢，你如果跟这个 Fensock filter 去比的时候，你会发现它这边所写的正负号跟前面其实有矛盾啊。那这个东西其实蛮容易解释的，就是一个人在写书的时候，虽然我们前后两节。 在后面跟着五十，在写书的时候，不见得是写完53那些50，你有可能写到后面，你才觉得好像有必要把50加进来，就加了一个50，但那时候你可能隔了2个月，但是你那时候头脑的状态跟2个月前不一样，所以你可能正负号就会反过来 ，OK， 这个蛮正常啊，因为那个我自己也写过书，所以我也晓得这样的状况啊。那这个正负号的差别在于。 数学上有一种叫主动旋转跟被动旋转啊，一个是坐标轴在转，一种是真的把向量转。然后有时候你头脑中你想的是主动，然后写的是被动啊，或者想的是被动，写的是主动，你就可能造成这个正负号反过来啊。那但这个都不是很严重的事情啊，反正就正负号颠倒过来就好了。So here are some difference about the sign signature, different from the result listed in the textbook. OK， 好，那我们现在呢，再来看看这个怎么去计算这个结果啊。So now we try to calculate this limit. Here W0 is we see that since now gamma denotes the total retardation, so the retardation for one piece of wavelength is this quantity divided by n. So for one piece we have retardation equal to gamma over n. So we substitute this gamma of n into the formula of W0 and we find that the result is minus gamma over n. 0, 0 is the measure I gamma over 3. Okay. Then you can write down this W0 and calculate W0 times R positive 5 over n. Here R positive 5 over n is equal to this quantity. this matrix. So you can multiply W0 with this R positive phi of n and calculate the n power using the Chebyshev identity, and then multiply the result with R minus phi to get the final n matrix. And here, so here we need to calculate the n power. N is R minus phi times the n power of this matrix. Then if we need to calculate this result, we should define cosine theta as 1/2 of the sum. Okay, and this gives us cosine theta equal to cosine phi over n and cosine gamma over 2n. Okay. So this theta is the theta for one piece of the wave plate, which is a very thin layer of the liquid crystal. Okay. And remember that since phi over n and gamma over 2n are both small quantity, so we can write theta as can be approximated by this phi over n squared plus gamma over 2n squared. Okay. And we can approximate, we can denote this as capital X over n. Okay. Then what is X? So this means X is equal to square root of phi squared plus half gamma squared. Okay. So we can define a quantity called capital X. And this means that the final result might be able to be represented by this capital X. So now we calculate the result. So n is equal to R minus phi times, we see, according to Chebyshev's identity, we have this A. What is A? This is A. This is A. This is A times N theta is capital X. Okay. And minus sine n minus 1 theta. N minus 1 theta means x minus this 1. Okay. And over sine theta. Sine theta means this. And similarly, this part and here we have B is this. B times minus this is the result obtained according to Chebyshev identity. Okay. Now we need to remember that now n is approaching infinity. Then what will be the final result? Okay. So when n is so large that now cosine, if we keep since in the denominator, the order of the denominator is when n is very large, then sine x over n can be approximated by x over n. We keep up only to the first order. Okay. Then if we keep only to the first order, then cosine y over n becomes 1, because the first difference comes from the second order. Okay. And now we keep only up to the first order. And this exponential minus I gamma over 2n can be approximated by 1 minus I gamma over 2n up to the first order. Okay. So we see that and how about this? This is equal to sine x cosine minus cosine x sine. It now becomes sine x minus x over n cosine x. Okay. So now we substitute them into this expression. Divide minus okay, and this gives us here this side x cancel with this side x, and and now this minus I gamma over 2n sine x plus x over n cosine x over n is equal to cosine x minus I gamma over 2x sine x. Okay? So this part becomes cosine x minus I gamma over 2 sine x over x. Okay. And similarly, this part, which is the convex conjugate of the 1 element, with cosine x plus I f gamma sine x over x. And now this replaced by x over n, this can be replaced by phi over n, and n, 1 over n can cancel each other. Then this becomes this. Here the first order term does not appear because we keep the ratio final result to the 0th order term. So this becomes this becomes okay.好，这个就是我们所要用到的公式。好，那这边的 r 负 phi 是什么东西？好，这个 r 负 phi 它所做的事情是这样。好。This matrix rotate the vector by angle phi. Okay. R positive phi is represent we rotate the coordinate axis by angle phi. But R minus phi means we keep the coordinate axis fixed but rotate the vector itself by phi. OK， 就是一个所谓主动跟一个被动啊，或者你可以看成是把坐标轴往负 phi 方向转啊，就转到负 phi 的地方，就相当于是我们把向量相对于这个坐标转一个 phi 啊。那好，所以这个矩阵呢 ，this matrix rotate it rotates the vector by angle phi. 如果你把它乘以任何的 vector， 它就转那个 vector， 转一个 vector。好，那现在好玩的情况是这样，就是说，假如伽马很大，就伽马跟 phi 比起来，伽马也大于 phi 的话 ，retardation 如果比这个 rotation angle phi 大非常多的时候，那这个东西就会进一步近似成一个很简单的样子。So we now consider the so-called adiabatic following. This situation means that gamma is much larger than phi. 就是整个液晶层的厚度呢，它所提供的这个 retardation 呢，比那个表面上转的角度大很多。So when this happens, we see that x is this quantity will be approximated by half gamma. Okay. So when this happens, half gamma is approximated to x, and these two parts cancel with each other. So this can be approximated by cosine half gamma minus I sine half gamma. Okay, and which is nothing but exponential minus I half gamma. Okay, so this becomes m equal to r minus phi times exponential minus half gamma 0 0 exponential I half gamma. Okay. When this condition is satisfied, we have a very simple result m can be approximated by this matrix. Then how to use this matrix to predict some results? So suppose originally we sent a line polarized along the x direction. The first layer of the molecule is also aligned along the x direction. Then we multiply m to this vector. This gives us r minus I times this.那我们现在这个结果呢，其实就等于是怎样？就是连续的去旋转这个向量，So m originally we have b equal to 1, 0. Then finally we have b prime equal to m times b. Then this is just equal to minus half gamma times r minus phi times 1, 0. And this is nothing but this simple result. Okay, this is just originally we have this correlation. X correlation. Then finally we have this correlation. So this means that this block of liquid crystal rotate the correlation vector gradually and finally rotate it to the final angle phi 就是你现在呢这个等于是这个如果是这个情况发生的时候就是伽马远大于 phi 的时候，伽马远大于 phi 的时候，那这块一晶所扮演的角色，就是把你原来的 correlation 连续的旋转转到新的角度，转到那个一晶分子最后的那个角度，就这样这样那如果我们考虑的不是这个极端状况，而是一般状况的话rotation. So if phi is equal to f pi, and if we substitute it into this matrix, then finally, if originally we have x polarized light, then finally we get this phi sine x over x cosine x minus I f gamma sine x over x. OK， 好，那我们也可以用这个同样方式去分析它的这个 transmittance。We can use the same strategy to analyze the transmittance. And finally, we get the transmission formula as this one. Sine squared f pi gamma 1 plus gamma over pi squared. One plus gamma over pi squared. Okay. Remember now this gamma is the total retardation. Okay, not the retardation for one single layer. Okay. 这边跟前面 FET-SOAK filter 有一点点不一样，是说FET-SOAK filter 呢，你其实会出现很多次同样形式的这个主峰重复出现，但这边只有一个，因为呢，你现在是把 n 取成连续极限的时候相当于是从一个主峰到另外一个主峰之间的间隔拉得很远，远到另外一个看不见 ，OK， 好，太远，那所以你当真正无穷的时候，就是移到无穷远去，所以呢就只有一个，只有一个主峰，但它旁边的那些小 peak 是有的，So here we have only one main peak. 一个小问题呢，是在5至5节提到的，就是说你真正观察到的情况啊，其实没有这么平滑的曲线，而是呢，这里会有一些毛毛的啊。那些东西怎么来的呢？其实这个道理呢是我现在不是讲易经了啊，我现在讲如果是在这种filter啊，出现一些毛毛的这个刺一样，这个其实就是Fabry-Pérot 的效应啊。那个原因呢，其实是因为我们真实的 wave plane 其实还是会有一些反射。好，那我们在前面讲到说，我们把 wave plane 数学描述当成是unit parametrics， 其实是把反射完全忽略掉。但如果反射考虑进去的时候，你就会发现它其实会有这些内部的震荡啊。那些震荡其实就是内部的反射所造成，多重反射造成。好，我们这边先在这里休息一下。我现在解释一下这个字啊，这个字是非常反叛的意思啊。This word, diabatic means very slowly variation. Okay? So, for example, in thermodynamics, you also encounter this word, diabatic something, okay? Which means you move very slowly without changing the balance, thermal balance. Okay? And in quantum mechanics, you can also, for example, you change some variable very slowly without perturbing this system. So the electron can stay at the same energy state, okay, but only change the parameter. Then if you change the parameter and change it back to the original parameter, you get some extra phase called Fabry phase, which is a very interesting study topics. Okay, 好，那所以这个是非常反叛的意思。So this word implies that gamma is much larger than phi. Okay, only under this condition can we get the simple result like this. And if you now apply an external electric field along the z-axis, then the retardation disappears. Then the light can penetrate through the whole structure. So you can apply or turn on or turn off the electric field to control the transmittance of this device. Then can use this principle to design the so-called liquid crystal display. 所以你可以用这个加电场的方式，加电场或把电场去掉的方式呢，去控制它的 transmission。那再来呢，就是在这个最后一节，我刚才也提到一点点5.5 section, the problem of Fresnel reflection and the phase shift. If we consider fan or soft filter, originally we have this kind of T-curve around the peak. However, if we consider the Fresnel reflection, then the result becomes this. This is caused by the internal reflection back and forth, okay, in each layer, okay, and we ignored or neglected them because in the discussion we assume there is no reflection by the waveplane. So under this assumption, we can identify the mathematical description of waveplane as pure unitary matrix. However, if you consider the possibility of internal reflection, you cannot use that simple description, the 2 by 1 vector and the 2 by 2 matrix as the waveplane. You should replace them by, say, 4 by 1 vector. For example, right, left, and x, y. Okay. A 4 by 1 vector can be used to describe the polarization. In one layer, we have wave propagating toward the right and then wave propagating toward the left. So we can separate them as the components here and components here. And besides, we have the x polarization and y polarization, which can be denoted as x, y, x, y. So this becomes a 4 by 1 vector. And the matrix of waveplane now becomes a 4 by 4 matrix, a 4 by 4 matrix. Okay? Then if you use this kind of formulation to calculate the result, you finally find the result becomes something like this. Okay? This is caused by the so-called Fresnel's reflection. Okay. 好，那我们现在把这个第5章的作业投一下，好。然后回头教一点第4章略过的后面的部分，啊，然后我们就尽快连到第7章。Homework。勾这5啊，勾这5。然后我们现在回过头来看第4章。Now I go back to chapter 4, 4.9. Optical activity， 光学活性。那光学活性指的是什么呢？其实是这样，就是说in most of the discussions in chapter 4, we assume that light inside the medium, although its polarization might be influenced by the crystal axis, and we can find some interesting behavior of light propagation. However, we always assume the polarization inside a medium to be linear polarization. This is not. This is in fact not truth. In fact, some materials, the light propagated in some materials can have elliptical polarization. OK， 就是在某一些这个材料里面呢，光实际上正常的传播状态，它并不是线变振，而是椭圆变振，或者圆变振。So, for example, in what if you consider a glass of water containing some sugar, then the existence of sugar can have the effect that rotate the polarization of the light. 就是说会让它变成这个圆变振。So, suppose we consider a medium which it can rotate the polarization of the light. 这边我们并没有要求要像什么刚刚易经那样什么分子转来转去，或者是wave plane 那样那个 soap filter 那样子人为去安排这些转来转去，这就是一个完全均匀的材料，它本身就可以让光的偏振转来转去。好，那它转来转去的原因不是因为我们刻意把分子轴向或什么做了旋转，而是在这里面传播的光的正常的状态就是椭圆偏振或者圆偏振。OK， 好 ，So we have just talked about how to rotate the polarization of the light by using some device, for example, soap filter, fan soap filter, electric liquid crystal, etc. However, now we will see that there is the possibility that some medium, homogeneous medium, okay, if we consider a wave, electromagnetic wave propagating inside this medium, and we just like to find the natural polarization state inside this medium, just like we did before in chapter 4, then we will find inside this some kind of medium, the natural polarization state is elliptical, okay? Elliptical polarization or circularly polarized light inside this medium. So, if we send a linearly polarized light into this kind of medium, then since linear polarization can be written as superposition of two different circularly polarized light, then for these two circularly polarized light, we encounter two different refracting distances. So after penetration through this crystal, the final polarization state can also be changed by this crystal. Okay? 好，那这个情况是因为它里面天然的这个偏振状态就是圆偏振或者椭圆偏振。好，那所以这个情况会是这样哈。So this is just like this. Originally we said the beam light polarized upward, and we denote this as the x-axis. And the propagation direction is along the z-axis. Here, this is the y-axis. Then you will see that the polarization being changed gradually. And final polarization may be different from the original polarization. Okay? So, so we can write this result as, say, originally we have x for polarized line. X can be written as 1 over square root 2 r plus L. Here, R is this. L is this. Okay, R denotes the right-hand circularly polarized line. L denotes the left-hand circularly polarization. Circular polarization. Then the sum of them give us X polarization. Okay, and for the right-hand circularly polarized light propagating inside this optically active medium along the z-axis, it can be described by this. This you see this, I can denote this as say ER. Okay. Here KR is omega over C times NR. Here R means R means right hand. Right-handed. Okay. Right-handed circulating polarized line. Okay. And for the left-hand component, we have L times EXP I omega t minus KL times C. Okay, here KL is omega over C and L. Here L means left-handed.那我们对左旋跟右旋有不同的折射率不是像我们之前那个是对，比如说 x 偏正跟 y 偏正有不同折射率，我们现在是对左旋跟右旋有不同折射率那这时候呢，经过一段距离之后，它会叠出什么来？这边稍微改一下，这边改成D，代表它的长度。这边我也乘上一个 D0。然后我们现在要计算这个，把它叠加起来会变成这个其实是在 z 等于0的地方是 x 变正，那我们要看一段距离之后， 边还是把它除以根号2啊。来写。对，好。We denote the sum of the total field. Okay. So originally, at z equal to 0, we have this equal to b0 over square root 2 times exponential I omega t times r plus L, okay, which is nothing but d0 times x times I omega t times x 好，在 z 等于0的地方长这样。好，那现在呢，我们看 z 不等于0的地方，它会变成什么样？好。So now we consider z arbitrary z. For arbitrary z, this summation, this superposition gives us d0 over square root 2 times exponential I omega t times 1/2 the average of KL and KR is minus 1/2 I KL plus KR times Z times R exponential minus I KR minus KL over 2 times Z over 2, okay, plus L exponential positive KR minus KL Z over 2, okay, and and this is just equal to Z times this one X minus IY times I omega NL minus NR Z over 2C plus X plus IY EI omega NL minus NR Z over 2C. Okay? This is an angle. Okay? Minus. Okay. So if I call this theta, exponential I theta plus exponential minus I theta divided by 2, the product of these two factors gives us 1 over 2, give us cosine. Okay, and exponential I theta times minus I plus potential minus I theta times I is equal to minus I times this minus this. Okay, and the minus I means divided by I, and over 2, this gives us sine theta. Okay, so this is equal to this d0 times this exponential I omega t minus z times nr plus nl over to c times p, a unit vector p. And what is p? P is just this one. P is x unit vector times cosine omega nl minus nr z over 2c plus y omega nl minus nr times z over 2c. Okay. So this means that originally we have X polarization state, and finally we have P polarization state. And what is P polarization? The rotation angle phi is equal to this. OK， 好，就是你走到传播到 z 的地方的时候呢，这个偏振就会转到这个 phi 的角度，这个 phi 呢是什么？是这个数字。那你可以再进一步把 omega over c 改成用波长来表示的话，omega over c is just the wave number or wave vector length in the vacuum. So it is just equal to 2 pi over times this nl minus nr times z over 2. Okay. So this is equal to pi over lambda times nl minus nr times z. Okay. So the rotation angle is this one. Okay. So we can define a quantity called rotatory power. Rotatory power. Rho is defined as the rotation angle per unit distance. Okay, so this is nothing but this one. Okay, this is the so-called rotatory power. 这个就是 rotatory power 就是对于这种有所谓的 optical activity 的有光学活性的材料里面会有这样一个参数叫 rotatory power 每单位 传播距离转多少角度？好，就是这边所介绍的这个东西。那通常这个NL 减 NR 的值其实非常小啊，非常小，但是你给它够长的距离的话，它还是可以转到蛮大的角度啊，比如说这个 quartz 啊，它的这个让达在6328 Armstrong 的时候，它是每公分188度啊，所以其实也算是转蛮多角度的啊，那看你用多长的距离去看啊。好，那现在呢，如果我们要从物理的机制上去解释这个optical activity 是怎么来的话，大致上可以这样想啊。So now we see that some material has this property that it can rotate the polarization vector of the wave. However, what is the mechanism, what is underlying physics, which can be used to explain this property? You can think like this: the molecule of optically active material typically destroy. It has no parity symmetry. Okay, which means that the molecule, you can distinguish the molecule to the left hand molecule and the right hand molecule. Okay. 就是说你可以分成什么左手旋进的分子或右手旋进的分子啊。So you can distinguish the molecule by right hand circular molecule, left hand circular molecule. If one kind of helicity is dominant, then you will have this property. So suppose I imagine the molecule to have a shape like a solenoid. Suppose we have molecule whose shape is like this. Then typically, we know that if we apply electric field, we can polarize the medium through two mechanisms. The first mechanism is that we can rotate the dipole inside the medium. The other mechanism is that we can change the shape of the electron cloud. Okay, so we can polarize the distribution of the electron. However, there is the third possibility, which means suppose we consider a circuit like this, then if we apply electric field in this way, then we can separate positive and negative charge. So here becomes positive polarized, here becomes negative polarized. So we have a dipole along this direction. However, we can also polarize this molecule by considering time varying magnetic field. Okay. Suppose we have this. This means that if this can be treated as a circuit, then we have induced the electric field along this circuit. If we change the magnetic field, okay, then this can also help to polarize the molecule this way. Okay, so we have two mechanisms to contribute to the dipole. So the dipole can be written as alpha times E plus minus some beta times h dot. Here dot means time variation of time. You must change the magnetic field in time, so you can have the induced electric field applied to this molecule to help polarize it. Okay, then this contributes to the so-called polarization in the D vector. D vector. Okay. For a single frequency situation, we can replace this by this. Okay. So this means that the contribution from time varying magnetic field contains an I factor, and its mathematical distribution can be written like this. Since this corresponds to curl E, okay, because Faraday's law, curl E is minus partial T, okay, and this for a plane wave we have K. This becomes K cross E, okay, K cross E. So here we introduce a vector parallel to K. We denote it as G vector. G vector. G vector is along the direction of the K vector. And we denote the contribution as this. The contribution caused by changing magnetic field in time contribute to the electric polarization can be written as this. Okay, 那这里面其实有很多的细节，当然我们不可能在这本书里面去把它讲清楚但是呢，你大致从直觉上可以猜得到。它的形式大概长什么样子比如说像我刚才说，这边它跟磁场的时变性有关，然后磁场时变性对应到 curl E， 所以就会跑出这个 cross 出来。然后呢，对一个平面波来讲呢 ，cross 呢，这边 curl 呢会变成是 cross 然后这个方向留下来，但是这个是跟物质的特性有关这个 G。然后这边这个 I 从哪里来？是跟这个时间的微分有关那总之会贡献一个像这样的东西在 P 里面So finally we have this D vector. The D vector can be written as epsilon E plus I epsilon 0 times G vector cross E. Okay. If now the G vector goes to 0, then we reduce to the result reduced to the original results we already familiar in chapter 4. But if G is included, then we can use this expression of the D vector to discuss the effect of particle activity. 就是如果 要考虑这个光学活性的时候，我们 D 就会改成这个形式。好，那这个形式里面的第二项呢，是对应到比如说跟磁场变化有关的那些贡献。好，然后第一项呢就是比较原来的那种贡献。好，那这部分其实贡献很小，这个部分通常它很小，但是如果我们要实际考虑它是要加进。好，this part usually can be much weaker than this part. However, if we want to discuss the effect of optical activity, we should include these terms. OK， 好，那接下来我们就来探讨一下数学上要怎么去描述它，然后呢，怎么去算出我们要的结果。So the author used a trick that he had already used in discussing the so-called index sinusoid. Okay, the trick is that we can construct the matrix corresponding to this G vector. Okay, the method is that you see. Suppose we consider something like this, A cross B. Then you see what is A cross B. Suppose A, we know the three components of A is AX, AY, and AC. The three components of B are BX, BY, and BC. If this result is C, then what is CX? CX is AY BC minus AZ B1. Okay, and CY CX minus X Z CC CXY. So you see, I can write this as BX, BY, BC. And CX is AY, BC minus AC, BY. So AY, BC minus AC, BY. Okay. CY is AC, BX minus AX, BC. And CZ is AX, BY minus AY, BX. Okay? So this means I can define A matrix to replace this operation. This operation, this action, A cross something, can be replaced by A matrix. This is the A matrix. Okay. So now we can define the G matrix, G cross E, G So the G matrix are defined as just like this here. 1 and 2 components correspond to the minus third component. Okay. 1, 2 is minus G3. Okay, and this is minus 1. And 2, 3. G1. 3, 1. Okay? So this is the G matrix. This is the G matrix. G 的1, 2, 3就是 x, y, z 所以这边就是 1 is x, 2 is y, 3 is z. Okay, so this is the G matrix. Then using the G matrix, you can write this as this. Here, this epsilon is the epsilon tensor matrix without considering the optical activity. And when it adds to the this contribution, then the whole matrix we can denote it as epsilon prime. Then now epsilon prime contains the effective optical activity. Okay, so we can write epsilon prime as epsilon prime can be written as epsilon plus I epsilon 0 times the G matrix. Here G vector is magnitude times the unit vector along the propagation direction. Okay. So if you use this epsilon prime to replace the epsilon matrix and rewrite the normal surface, then you will get the modified Fresnel's equation, right? This sx squared, sy squared, sz squared. Okay. Okay. This is the equation when we replace epsilon by epsilon prime and then rederive the normal surface equation, then we get this equation. I will not spend time to derive it, okay, but you should know there is some equation look like this. Then, since we have already introduced that we can multiply this vector to change this equation into a form like this. then you multiply these vectors, you will find that finally this can be written as A times this n squared minus n1 squared, n squared minus n2 squared is equal to A times G。好，这边就说这个是没有 G 的时候啊。When G is equal to 0, the original Fresnel's equation wave normal can be written as this. Then when G is not equal to 0, you multiply some factor, then finally we will find the equation becomes this one. Okay. Here, the n1 and n2 are the two eigenindices when there is no G. 就是我们原来所导出来的那个，从一个传播方向会有两个折射率的那两个折射率就是这两个那但是有 G 的时候就会变成这样的方程式那我们之后会利用这样的方程式去探讨这个它的影响那我们今天就先讲到这里。